adjustment so that it can send focused transmission to each one dynamically. Although the feedback process sounds straightforward, it is complex to implement. The 802.11n amendment allowed 4 different feedback mechanisms to be used. To date, no practical feedback mechanisms has been implemented due to compatibility issues among vendors and mechanisms. Cisco also offers Client Link, which performs a similar transmit beamforming function. However, Client Link does not require explicit feedback from an 802.11n device at all. Based on data that is received from a far-end device, the phase value can be calculated and performed on data transmission that are returned to it. In this case, the far-end device can be 802.11n or legacy 802.11a or G. The next feature related to the improving the reliability of the 802.11n is the maximal ratio combining or MRC. When an RF signal is received on a device, it may look very little like to the original transmitted signal. The signal may be degraded or distorted due to a variety of conditions. If that same signal can be transmitted over multiple antennas, as in the case of a MIMO device, then 802.11n can attempt to restore it to its original state. An 802.11n device can use multiple antennas and radio chains to receive the multiple transmitted copies of the signal. One copy might be better than the other, or one copy might be better for a time and then become worse than the others. In any event, 802.11n offers maximal ratio combining or MRC, a feature that can combine the copies to produce one signal that represents the best version at any given time. The end result is a reconstructed signal with an improved SNR and receiver sensitivity. Alright. About the 802.11n modulation and coding schemes, recall that 802.11g and 802.11a are both based on OFDM and can use binary phase shift keying or BPSK, quadrature phase shift keying or QPSK, 16 QAM or quadrature amplitude modulation, and 64 QAM modulation schemes. Depending on conditions affecting the RF signals, wireless devices can choose one of the 8 possible modulation and coding schemes. The 802.11n amendment is somewhat backward compatible with 802.11a and 802.11g, as it supports the same 8 schemes. However, as the schemes are applied to an increasing number of spatial streams, the number of combination multiplies. 802.11n support a total of 32 possible schemes, 8 per spatial streams, so many that they are known by a modulation and coding schemes, okay, MCS index number. Beyond that, channel aggregation and guard interval selection add even more variables to the mix, okay. In all, 802.11n has 128 possible data rate, okay, and for reference we can use this table. As you can see here, we have multiple conditions, and for example, this is the MCS index 0 to 26, and then 21 to 31, 31 equal to the 32 MCS index or modulation and coding scheme index. And here you can see different spatial streams 1 to 4, and after that we can see modulation and coding from BPSK to the 64 QAM. And if you have guard, here you can see we have 20 megahertz channel with guard interval 800 nanosecond, then 40 megahertz channel. This is the channel aggregation with again 800 nanosecond guard interval. And here we have the same for example channels, okay, 20 and 40 megahertz, but with guard interval 400 nanosecond. As you can see, when we have for example 40 megahertz channel with guard interval 400 nanosecond, in the 64 QAM 5/6 we can reach to up to 600 megabit per second data rate, okay. Because of that, here we have different conditions, and for each according to the conditions related to the number of spatial streams, related to the modulation and coding scheme, related to the channel aggregation, and also guard interval. We can reach to different data rates. As you can see here, we have multiple different data rates in the 802.11n. The next technology of the IEEE 802.11 standards is 802.11ac. Okay, the many features and high throughput of 802.11n might make it seem like the end-all wireless LAN technology. As with most any aspect of computing, the current state of the art is never good enough. The 802.11ac amendment finalized in 2013 takes the best of the 802.11n and offers a new generation that is much faster and more scalable. The goal is to bring wireless on a par with gigabit Ethernet through a set of capabilities known as very high throughput or VHT. Once 802.11ac is fully implemented, it should support a maximum data rate of 6.93 gigabit per second. Some of the most notable improvements are outlined in the list that follows and further described in the ensuing sections. As you read or as you learn through the improvement, you might notice that they sound familiar from the list of 802.11n features but are greatly enhanced. First, better channel aggregation. 40 megahertz bonded channels can be bonded again into channels that are 80 or 160 megahertz wide. Because of the extensive use of channels, 802.11ac can be used only in the 5 gigahertz band. More dense modulation. 256 QAM is used to modulate the RF signal in 256 different ways, taking more data at one time and boosting throughput. MAC layer efficiency. More data can be aggregated with less overhead. Explicit transmit beamforming. To simplify and scale transmit beamforming, only a single feedback method is supported. Scalable MIMO. Up to 8 spatial streams can be used. Multi-user MIMO or MU MIMO. An 802.11ac access point or AP can send multiple frames to multiple receiving devices simultaneously. Let me to explain a little about these features about the 802.11ac. Alright, now let me to explain about the robust channel aggregation. The 5 GHz band is made up of many channels, each one 20 MHz wide as illustrated in this figure, where 802.11a must always use 20 MHz channels, as you can see here. One improvement with 802.11n is that 2 channels can be aggregated, forming a single 40 MHz channel to increase throughput. The 802.11ac amendment support an even better channel aggregation scheme where the channel widths can be 20, 40, 80 or 160 MHz. As always, to support efficient roaming and to minimize neighboring channel interference, the channels should not overlap. With 23 available channels, the number of non-overlapping aggregated channels decreases as the channel width increases. For example, there are only 11 40 MHz channels, 5 80 MHz channels, and 2 160 MHz channels are available. To maximize channel use, 802.11ac offers something really clever. The channel widths can vary dynamically on a frame-by-frame basis. This means that wide channels can overlap within the band but cannot be used at the same time. Every transmission does not normally require a wide channel, so the channel space can be negotiated for each frame. If a wide channel is needed and is currently available, it can be used. If some fraction of it's already in use, then the remainder can be claimed for a transmission. Suppose two APs are located in the same general area as their cells overlap. Ideally, the two APs should operate on separate non-overlapping channels to minimize co-channel and neighboring channel interference. As the channel layout in this figure, shows, the two APs can use their assigned 20 and 40 megahertz channel at any time without